Okay, shut up now. Um, last time we went over the syllabus and stuff. Today I want to go through a detailed outline of what we're going to cover in this class, what kind of stuff to expect. I'm going to try to, as the class goes on, keep bringing up the outline so you can sort of keep reminding yourself where in the overall flow of things we are. And then I'll give four common misconceptions. I think I mentioned last time that physics 1 compared to physics 2 is all stuff that you kind of have intuition about. Like if you throw something, it arcs and hits the ground and whatever. And that helps in a lot of cases. But there are a few cases where people's intuition tends to be wrong. It turns out that the way people have thought about it for a long time is not correct. And so I have four of these things that over the course of the semester, I'm going to try to point out as places where you not only have to, like, it's not as easy as just going and learning the new thing. You actually sort of have to actively tell yourself, like, oh, all this stuff that I've been thinking about this is wrong. It turns out it's wrong. And that'll be it for today. And then it's Labor Day weekend. We won't get to anything far enough for you to do homework yet, so no homework over Labor Day weekend. And then on Tuesday, we'll finally get to some material and we can start to have assignments and stuff like that. Okay, so here's an outline of the class. We're going to start out by talking about units and unit conversions. Or let's call it units, unit conversions, and scientific notation. There are three basic unit types that every other unit in this class are going to be made out of. And it it doesn't actually have to be these three, but you can just say it as all the stuff that we're going to cover in this class can just be made as a combination of three units. The ones that I'm going to call the sort of fundamental units are length, time, and mass. Okay. So what does that mean that other ones can be made out of it? So like speed has units, say miles per hour. We're going to use meters per second more often. But that unit for speed is actually just a unit of length divided by a unit of time. And so we're going to deal with a lot of units that are just combinations. And we're going to talk about doing math with units. So like, for example, if you have an equation where you have to multiply mass times velocity, well, mass has its own units, velocity has its own units. What happens when you multiply these two things together? What happens to the units? So we need to get that stuff straight. And then conversions, like for example, we're going to do most of our stuff in SI units. So, velocity would be meters per second. But if you want to use meters per second and somebody gives you a velocity in miles per hour, you need to know how to go from one to the other one. So that's the first thing we'll start with. And then after that, we'll get into the first sort of physics topic, really, which is one-dimensional particle kinematics. the 1D, for our purposes, you can really just think of it as something moving along a line, although that's not, you can have 1D motion that isn't along a line, but I'll talk about that later on. So I'll say you can basically think of it as along a line. Particle, when you're treating something as a particle, you're not concerned about the orientation of it. So if I'm doing a calculation about this pin and I'm treating it as a particle, then I'm trying to calculate where it's going to be at this instant, but I don't care whether it's the cap is facing that way or whether the cap's facing that way. Okay, we throw out all the orientation information. It's pretty common for people to think of what does it mean for something to be a particle, and a lot of people would say it means that thing is really small. And there are reasons why you treat really small things as particles, but things don't have to be small to treat them as a particle. You know, I showed you this pen isn't small on like a physics scale or anything. And actually, when people do planetary motion calculations, most of the time they treat planets as particles, not because planets are small, but just because they're not trying to figure out whether this mountain over here is facing this planet or over this planet. They're just trying to figure out where the centers are. And so you can throw out all that information and simplify the calculation. And then kinematics means describing the motion without concern to the things that is causing the motion. So we won't deal with any mass and we won't deal with any force in kinematics. So the things that we are going to care about are time, position, velocity, and acceleration. So the reason that we start with one-dimensional motion is there's something easy mathematically about one-dimensional motion. If you choose the positive direction to represent one way along the path and the negative direction to represent the other way, so if you choose, if you choose one of those, you've by default chosen the other one. So let's just say if you choose a positive direction, then the sign gives the direction of the object is moving. Does that make sense? So like if you choose that positive is going to represent this way and then negative is going to represent that way, and then if you say the position is positive 10, that positive tells you that it's in the positive direction from the 0. And if you say the position is negative 4, it means that the object is 4 meters or whatever units you're using in the negative direction from 0. So that sign gives you the direction of these quantities. After we've talked about, we'll start talking about constant acceleration equations. And we'll talk about projectile motion. And when we're done talking about one-dimensional particle kinematics, we'll go into a little mathematical section on a topic called vectors. In order to do that, I first have to give a little introduction to some basic trigonometry. I know a lot of people, or most people in here, haven't had trigonometry in a class, so I have to talk about that, but we don't have to learn very many things about it. And the reason that we're going to discuss vectors is that vectors give a way to describe direction, to mathematically deal with direction in two-dimensional motion. Okay, so up here in one-dimensional kinematics, say that this is the path an object is moving along, and let's say that this is the object, okay? And let's say we're going to call this the positive direction and this the negative direction. So whether we say the particle's moving in the positive direction or negative, that tells us everything that that object can possibly do. All it can do is go in one direction or the other, okay? But that's not true anymore if a particle can move in two dimensions. So let's say this is a particle, and now it has all these choices, you know, infinitely many choices of directions to go. Well, you could call one of these positive and one negative, but that doesn't help you if you're going in any of the other infinitely many directions. So positive and negative as a way to describe direction isn't going to work anymore. Okay, and that's why we need this new mathematical thing. That's what a vector is for. You can think of a vector as an arrow, and it has two properties. It has a length and a direction. So, for example, if this is the arrow, the vector that represents some mathematical quantity, the length is whatever this is. You know, could measure it, or it'll just be specified in the problem. And the direction is just the way that it's pointed. And that direction can be anywhere in here. And we'll see that it's one thing to just describe what this vector is, but we'll see that doing math with vectors ends up being pretty simple. And once we're done defining vectors, learning how to do math with vectors, then we'll get into two-dimensional particle kinematics. So now the thing you can think of objects as having a lot more freedom to move in different directions. A thing can move anywhere in the plane. It's not moving along a line anymore. Particle still means that we're only concerned with the location of things, not its orientation. And kinematics still means that we're describing motion, but not dealing with causes of motion. And so we're still just going to be dealing with time position, velocity, and acceleration. But now the difference is, instead of being signed numbers, position, velocity, and acceleration will all be vectors. Time hasn't changed. When you go to motion in a two-dimensional space, time is just telling you how long it's been since you sort of turned the stopwatch on, that kind of thing. So time is still just a number, and it'll always be a positive number, but these things are all going to be vectors now. And again, we'll do constant acceleration equations. But now it's going to be vector forms of these. And again, we'll deal with projectile motion. But now, instead of in one-dimensional projectile motion, we're confined to things either being launched straight up in the air or straight down. Now we'll be able to do calculations with things that are shot out at an angle. Question? Oh. Any questions about any of this so far? Then after we're done with two-dimensional kinematics, we're finally going to get into, so kinematics doesn't deal with any of the causes of the motion. It doesn't deal with mass, force, energy. Now we're finally going to get into the causes. And so this is going to be, we're still going to be in two dimensions. We're still going to be dealing with particles. And the combination of kinematics with the causes is, this is a ridiculous name, I don't know who chose this, but kinetics. It's like almost identical to the other one. I don't see the point of that, but I don't get to choose. So kinetics is kinematics combined with the causes of the motion. And those causes I'm going to think of as mass, force. Those are really the only ones for us in this section, although later we'll see that energy we can think of that way too. And the first thing that we're going to deal with in kinetics is called free body diagrams. These are just simple drawings that show all the forces that are acting on an object. All the forces applied to the object that you're treating as your system to analyze. And there are 4 different types of forces that we're going to consider. Every type of force that we'll deal with is going to fall somewhere in this set of 4. The first one isn't really a category, it's just itself, but it's always there. Weight. Weight is the force that's applied to the object by gravity. The second category is pushing forces. The third category is pulling forces. And the fourth category is friction forces. Okay, so everything we're going to see is going to fall into those four categories. And each of those four categories is going to have to be treated in sort of a specific way. Okay. And after we're done talking about how to draw free body diagrams, we're going to get into sort of the heart of kinetics, which is Newton's laws. And Newton's laws you can think of as giving the relationships between force, mass, and motion. So how do you know if you apply 150 newtons of force to an object with this mass, how do you know what it's going to do? Okay, that's what we're using Newton's laws for. And there are two Newton's laws that are going to be important for us in doing calculations. The first one is Newton's second law. And that's the most important equation in this whole class. You might have heard this before. This is the one that says F is equal to mass times acceleration. And the second most important equation in this class, or the second most important relationship in this class, is Newton's third law. And Newton's third law, we'll talk about how to treat it mathematically. This doesn't really help too much with how to interpret it in a mathematical problem, but you've probably heard this before too. This is the one that says for every action, there's an equal and opposite reaction. Okay. There's obviously a Newton's first law, but it's not actually helpful in calculations. We will talk about it in lab because intuitively it's sort of a helpful thing, but mathematically it's actually contained in Newton's second law. So there's not really any reason to treat those as separate things. Newton's second law contains Newton's first law and some other stuff. So we'll just go with that. Okay. And after we've introduced these laws, we'll talk about a specific type of motion where we have more information, and that's circular motion. And circular motion, we can break that up into two categories that we're going to treat differently. Uniform circular motion, where the speed is constant, and non-uniform circular motion, where the speed changes. But the basic idea is that if we know something's moving in a circle, that's enough for us to calculate a lot of important stuff about acceleration. And then we can use that with our kinematic equations. So I'll just say, if you know something's in circular motion, you know extra stuff about it, and then you can use that to solve for other things that you want to figure out. Okay, so that's the end of two-dimensional particle kinetics. And after that, we're going to go on to conservation laws. This is number 6. Conservation just means something stays the same over time. That's maybe not exactly the same meaning as we use in kind of everyday speech. You know, if you think of somebody who plants a lot of trees as being a conservationist, well, conservation in science means things stay exactly the same. So if you're planting extra trees or whatever, that's not exactly this meaning of conservation. But there are a few properties in physics that under certain conditions, no matter all this crazy stuff can happen, but these certain measurable things don't change as things bounce into each other and roll around and whatever. And a lot of times those can be useful. The first one of those is conservation of linear momentum. And we'll pretty much only use momentum in calculations for collisions and explosions. So if you have a problem, I think in this class, the only problems that I have in the practice problems are collision problems. But so if you have two things colliding, you're going to want to use conservation of linear momentum. If you don't, you're going to want to use something else. And the second conservation law, the more important of these two, is conservation of mechanical energy. And conservation of energy is one of the most important in all of science, one of the most important universal laws that there is. Conservation of energy always holds. But there's a lot of different kinds of energy. There's kinetic energy, potential energy, there's electric potential that develops energy, there's internal energy that's related to temperature. There are lots of ways to transfer energy around. And not all of these are mechanical energy, but in certain cases, if you don't have changes in temperature and other important things going on, you can simplify this universal law of conservation of energy into a conservation of mechanical energy, and we'll see that that simplifies some problems a lot. So we'll talk about that. We'll introduce the idea of force fields. It's a cool name because of Super Friends and stuff, but it doesn't end up being as interesting as all that. And anytime you're dealing with a force that can be described as a force field, those have what's called potential energy. And so we'll talk about how to calculate potential energy. And we'll see that conservation of mechanical energy is usually going to be useful when you're trying to find a relationship between an object's position and its speed. So what this gives is a relationship between position and speed. If you're trying to find something other than position and speed, then probably you're going to want to go a different direction with that kind of problem. And then after conservation laws, the last topic that we're going to get into is rigid body motion. And what's different in rigid body motion is this is the first time in the whole class that we're going to be able to do calculations involving orientation. Okay, and there are a lot of cases where that is a very important thing to know, and we'll get into that. But so this is the first time that we won't deal with things as particles. We won't treat our objects as particles. And therefore, it's the first time that we'll consider the object's orientation. Okay, so like for example, if you applied a really big, it would have to be a really big force because this is a heavy table. But if you applied a really big force to this part of the table, okay, you could treat that as a particle and calculate where the table would go. But all you'd be calculating is where the center of mass of the table would go. It would just tell you that it would go this way some amount. But there are a lot of applications where it's significant to know that if you hit this really hard, the table would spin as it went that way. You know what I mean? And so that's what we'll be able to do calculations about when we get into rigid bodies. Anybody have any questions about anything in that outline? That's pretty much the whole class. If we get done early, I might talk about a couple of other things, but this is all the stuff that you're going to be responsible for problems on or anything like that. No questions? Yep. Yes. The MCAT. Yeah, I'm pretty sure that Physics 2 is on it too. I think so. By the way, if anybody, if you're uh, like getting ready to take MCATs or something like that, or you're starting to look at practice problems for MCATs, and you have something that doesn't make sense to you, feel free to bring it in. I'd be happy to talk about it. Any other questions? Okay. So now I want to talk about these 4 misconceptions that almost everybody has that we're going to have to undo and then replace. So 4 common misconceptions. The first one, and I'm doing these in order of when we're going to get to them in the class. The first one is gravity does not make heavy things fall faster than light things. Let me reword that. Gravity doesn't make heavier things fall faster. This is a pretty ingrained feeling that most people have, that that if you drop something heavy and you drop something light, the heavier thing is going to hit the ground first. And so you sort of have this sense that gravity does something different to the heavier thing. Really, when that happens, when you drop a heavy thing and a light thing and the heavy thing hits the ground first, it really only has to do with air resistance. So that's just air resistance. And we'll talk about how air resistance affects different things differently. And I'll show a video of this amazing video where they have this giant vacuum chamber and they take all the air out of it so there's no air resistance. And they drop a bowling ball and a feather at the same time. And they both just fall like a bowling ball. They fall straight down, the feather hits the ground and bounces up into the air like violently. And that's because if you get rid of air resistance, gravity doesn't make things fall at different speeds. And that's not just, it's not just you all that have that impression. That's just about everybody does. And even, famous physicists from as recently as 400 years ago or something still didn't understand it, still believed that this was true. There was something about heavier things that made gravity accelerate them toward the ground faster, but that's not it. What it really is that under certain conditions, air slows some things down more than other things. Even that isn't really just about weight. If you think about like dropping drop a lead ball this big out of an airplane at the same time somebody jumps out with a parachute, okay? The person with the parachute is a lot heavier than the lead ball, but the lead ball would hit the ground a lot sooner because the parachute is designed to create a lot of air resistance, Anybody have any questions about that one? You're a liar. That's not, I'm waiting for someone to say that. This is all bullshit. I'll edit that out of the video. Okay, the second common misconception so I don't know about this wording. I'm not saying the misconception, I guess. I'm saying what's actually the fact, the horizontal motion of an object does not affect how gravity does not affect how gravity accelerates the object down. So the horizontal motion of an object doesn't change how gravity affects it. Okay, so this is also a very common thing that people tend to believe is like, if I held a bullet and gave it a little toss like this, it would go up and curve down and hit the ground, right? Everybody agrees that would happen. But now if I said, what happens if I hold a gun perfectly horizontally and shoot a bullet? Most people's understanding is the bullet is going so fast that it just continues in a straight line until it hits something. But that's not what happens. We sort of have that idea because when things are going really fast, they haven't dropped very much by the time they leave our line of sight. So to us, it looks like they're just going horizontally, you know? If you shot a bullet horizontally, it would hit the door at basically the same height that I shot it, you know what I mean? And so you'd be like, yeah, it just went in a straight line. But if you had enough room for the bullet to go without hitting anything, which would be a few hundred yards, and you held a bullet here and shot a bullet, like dropped the bullet straight down to the ground and shot the bullet perfectly horizontally, they would actually hit the ground at the exact same time. The one that you shot out of a gun would just hit the ground 400 yards away, so you wouldn't see it. And I'll show a video of an experiment like that, and we'll talk about it and stuff. But gravity does the same thing to objects no matter what the horizontal motion is. Anybody want to yell about that one? Okay, here's the third one. When two objects collide with each other, so in a collision, the size of the force that the objects apply to each other is always exactly the same. Okay, so let's think of a couple of examples where this seems impossible. Okay, so think about any collision where you would describe the collision as having a very clear winner and a very clear loser, kind of, you know. Like think about a home run hitter hitting a baseball, you know. So the ball comes in, there's a collision between the bat and the ball, and the bat and the batter look basically unaffected by it. Their swing just continues, but the ball totally switches directions and flies a couple hundred feet away, you know. So how is it possible that what this is saying is that the force that the bat's applying to the ball to make it go over the fence is exactly the same size of force that the ball applies to the bat? Okay, that doesn't feel right, but it really is true. And the only reason that the ball goes flying and the batter stays there rather than the batter going flying and the ball staying there. That would be a surprise. That would be cool if that happened like once every 10 times or whatever. Is because, so there's this force, this gigantic force. I'm not sure how big it is. Let's say it's 1,000 newtons, but that's just a totally made up number. So the bat applies 1,000 newtons of force to the ball, and that's enough to make the ball fly, 400 feet. The ball also applies 1,000 newtons of force to the bat, okay? But now here's where the difference is. The ball is in the air, so it's not being held by anything, and it weighs a handful of ounces. It's very light. And the bat weighs quite a bit, and it's being held onto by a 200-pound person, and the 200-pound person has spiked shoes connecting him or her to the ground, okay? And so all that together says that 1,000 newtons of force hitting that bat just doesn't change its motion very much. It has too many advantages once that force is applied. So the ball goes flying because it's a ball, and the bat doesn't because, and it does make sense if you think about the fact that, I don't know, for anybody who played, oh, well, none of you would have played baseball with wooden bats. I used to play baseball with wooden bats, so you would have broken bats sometimes, when I was like in 6th grade or something. And in 6th grade, if the pitchers throw 50 miles an hour or whatever it is, and if you get a broken bat, it just sounds a little funny, and you tap it on and you hear like a vibration, and you're like, the bat's broken. There's a little crack in there somewhere. But anybody know what a broken bat looks like in the major leagues? It does not look like that. The bat just explodes. Pieces go everywhere. People like dive out of the way in the stands and stuff. And the reason is that when a 50 mile per hour pitch comes into a 6th grader and the 6th grader hits it, the ball doesn't hit the bat with a lot of force. When the ball comes in at 100 miles an hour and a really strong 200-pound person hits it, the ball applies a ton of force to the bat, and if it hits it wrong, it breaks the bat into a million pieces. Okay, so this is a weird one, but this is all of these I'm saying, these are the things over the course of the semester. The way that you naturally think about this stuff has been wrong all these years, and we have to fix it. Yeah. Yes, exactly. Exactly. So what the deal is in that case just has to do with nothing but mass. So say there's 100,000 newtons of force in that collision, but if you apply 100,000 newtons of force to a little sedan, it goes flying. And if you apply 100,000 newtons of force to a truck, it doesn't change its motion very much. Yep. Okay, and this is the last one. This one actually, I feel bad ending on this one. This one isn't as cool as some of the other ones, but okay. In 2D and 3D, in 2 dimensions and 3 dimensions, things can accelerate without changing speed. And the reason for that is turning is also an acceleration. In 1D, there's no such thing as turning because you can only go along a line. And that's something that you're just going to have to sort of undo in your head too. The example that maybe makes sense to you about that, well, there's a couple examples. So think about like when you're in the car and you just realize at the last second that you have to turn, and you turn really fast, you get that feeling in your stomach. That feeling is acceleration. And even though, I mean, you would get that feeling even if the speed stayed exactly the same as you went around that turn. That drastic, rapid change in the direction that you're going is an acceleration, exactly the same kind of acceleration that you have when you speed up quickly or you slow down quickly. Okay. Anybody have any questions about that? I don't expect anyone to get too angry about that one. I was hoping the other ones, though. Okay, well, that went crazy fast, but let's stop there anyways. On Tuesday, we'll get into units, conversions, and scientific notation. And then finally, I'll give you assignments.